Welcome to my new calculus channel. Today I'm going to be talking about tangent lines and what they actually mean. Well, the concept of tangent was known a long time ago by the ancient Greeks, and they constructed it not only to circles and parabolas but to all sorts of conic geometric objects. So their definition of tangent was something along these lines. A tangent, took a curve, any curve, let's just draw a curve like that, is a line that meets the curve in exactly one place and crosses it nowhere. By the way, it's a finite line that meets the curve. It doesn't matter if later on that line had to go like that, because this particular point here isn't a point of tangency, so we're only dealing with this section of the line being tangent to the curve at this particular point here. Okay, so really a tangent line is a line such that it meets the curve in one place and extends to both sides of it, extends to both sides of the point, and crosses the curve nowhere. So it meets in one point, extends to both sides, and crosses the curve nowhere. Okay, nowhere. So this is what makes a line a tangent line, and this is what the Greeks thought of tangent lines, and in fact what everybody until Isaac Newton and Leibniz thought of tangent lines. So if we go to the Wikipedia moronic entry, which is written by a bunch of fools, they say here Euclid makes several references to the tangent. The word that you see inside there is a Greek word, and it's pronounced ephatomeni. In Apollonius's works, he also defines a tangent as a line being such that no other straight line could fall between it and the curve. Well, if that were the case, then the conical definitions by Leibniz, which we see here in the beginning, are really absurd. For example, Leibniz defined a tangent line as a line through a pair of infinitely close points. Well, what on earth does infinitely close mean? Well, if we have to go to that particular entry, infinitely close means an infinitesimal, and there is no such thing as an infinitesimal. It's junk. There are no infinitesimals. So, in other words, he defined it as something that depends on a pair of points that don't exist, because there are no infinitely close points. Ironically, if you look further down, there's something really amusing, because the person who wrote this article says that these methods led to the development of differential calculus in the 17th century, and it's oddly enough, it says here further developments were due to until the full theory of Isaac Newton. Well, neither Isaac Newton nor Gottfried Leibniz nor anybody before me had a full theory of tangent lines. They were morons, okay? In other words, they did not understand what they were doing. Isaac Newton did not understand, neither did Gottfried Leibniz, neither any one of these fools like Barrow, Wallace, however you pronounce his name, Hodge, and Desluce, and Roberval, not even Fermat knew, okay? None of the methods they used, this adequacy is just a bunch of rubbish. It doesn't really change anything, and it's not different to the finite difference method in any particular respect. So these mathematicians reached the full theory of Isaac Newton and Gottfried Leibniz. Well, that's kind of very funny, isn't it? Because Leibniz says that it's a tangent line, it rests on a pair of two infinitely close points. Right. That's absolute rubbish. And now here comes the blockbuster statement by the morons at Wikipedia Moronic. An 1828 edition 1828 definition of a tangent was a right line or a straight line which touches a curve, but which when produced does not cut it. That definition is correct. Okay? This old definition prevents inflection points. That's right, because there are no tangent lines at inflection points from having any tangent. It has been dismissed. Ha 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 ha. By who has it been dismissed? By the morons at Wikipedia or the morons in mainstream academia? That's just totally hilarious. But let's go back to this here and see what a tangent line again really is and what it is not. So, if for example a tangent line crosses the curve, then it is no different from any other line that actually crosses the curve. And the way mathematicians define it is in terms of the finite difference. So, for example, they'll say, move a particular secant from a given point all along like that, calculate it. Let me show you using the GeoGebra. That would be much easier. Okay, so for example, if you wanted to find the slope of the tangent line here, you'll just keep finding the slope of this secant, right? You see? And this secant will approach the slope of the tangent line, which is 1.00011. So as you get closer, what happens? That value approaches 1.001, right? Until you get right on the point. And also from this side, it approaches that value. The odd thing here is that the limit may not even be a number. It may just be a magnitude. So the limit, even though it may exist as a magnitude, is not a number. And there is no systematic way accepting the kludgy methods of Newton and Leibniz to arrive at the derivative, which is this 1.0011. So this here now has been defined as the slope of the tangent line. In other words, the limit of these finite different ratios. Okay, a limit of these finite different ratios depending on whichever side of the point you're coming from. So if you're coming from down here, that value will become more and more like the slope of the tangent line. This is also very circular because the derivative requires the tangent line and not the other way around. All straight lines have a slope or a gradient. It's their special characteristic. There's no other geometric object that has a slope. You cannot say this curve has a slope at every point of the curve unless you're talking about the slope of a tangent line. So the only geometric object with a slope is a tangent line. And this finite difference method here is very kludgy for the reasons I've just shown you. And what I'm going to show you now is what happens, for example, when you have a point like that, 1, 1, and there is no limit. I mean, some might think of this as an infinite limit, but there's no such thing as infinity, right? And so if you go over there, the secant slope isn't even defined. It's junk, okay? So you've got nothing once you overlap that point. In other words, the modern definition never defines the slope of the tangent line. And since you don't even know what the limit might be unless it's a rational number, it's really a very poor way of trying to describe a tangent line. Now, given this definition here, you'll notice that at this point, which is an inflection point, according to mathematicians, there is a vertical tangent there, but there isn't a vertical tangent. So they contradict themselves. They'll say that there is a vertical tangent and that there isn't. There's a vertical tangent there because this situation here is exactly the same. For example, a cubic. If you had to put that on 0, there's an inflection point there. And in this particular case, there is a tangent line going through that point according to the fools in mainstream academia. But naturally, of course, 0 divided by 0 is meaningless rot too, and in none of these examples can this definition here define the tangent line. It doesn't ever define the tangent line. it defines the slope of all the secant lines that are very close to this point. Okay, so going back to this again, this never defines a tangent line. As you can see, if you go there, that's also garbage. You know, I mean, what is 0 divided by 0? It's always 0 divided by 0. Let's take another example. Okay, so if you had to do that, overlaid exactly, let's put it on a point here. Yeah, and overlaid exactly, you see, it can't be calculated. 1 divided by 0. There happens to be a horizontal tangent line there, and also a vertical tangent line there, but there is no limit there, as you can see. Okay, so mainstream morons continue to propagate this rubbish, and it's rather amusing that they say it has been dismissed, and the modern definitions are correct. Dismissed by who? By which moron? Please do tell me which moron dismissed it. Nobody dismissed it. Okay, only some fools who run the academic trash heap decided that the proper definition of tangent didn't fit in with the nonsense they had come up with. So, as a result, the fools decided that a tangent line can now actually cross a curve at an inflection point. So if you have something like that, which is x cubed, they think now that there is a tangent line at x equal to 0. There isn't a tangent line. It's more like a half tangent line. Well, if we had to explode all these points here, we'd have something like this. We'd have points going like that, and a point right there in the middle, and then points like that. Okay, so you could easily have a half tangent there and a half tangent here, but there's no full tangent. And by very definition of tangent, a factomene in the Greek language means it touches the curve in one point and crosses it nowhere and extends to both sides of the curve. Okay, so strictly speaking, you can't even have a half tangent according to the original definition. It has to be a full tangent. And so mainstream morons have gotten this definition completely wrong. A tangent line is not defined this way. It is defined the way I explained to you here. It meets the curve in one point, extends to both sides, and crosses the curve nowhere. Okay, that is the correct definition of tangent line. That is the definition of tangent line that both Newton and Leibniz understood. Okay, the fact that Leibniz said, oh yeah, it has something to do with a line crossing through two infinitesimal points, that's just totally absurd. Okay, in other words, they're so close together, and if they're so close together, he's really talking about one point, isn't he? Yes, it's all meaningless nonsense, since there is no such thing as an infinitesimal. Coming back to this, so we've seen three examples now. We've seen an example of a circle which has vertical tangents and also horizontal tangents, by the way. And neither on the horizontal nor on the vertical does this definition here describe a tangent line. So it doesn't even work for the very basic conics. It doesn't work for other conics such as f cubed, right? Because if we go over there, it's also 0, and there is an inflection point there. I mean, it's undefined if you look there. Where there's a question mark, it means it's undefined, or meaningless nonsense rather. And the same story here with this lovely curve, which proves that academics want to have it both ways. They want to tell you, the monkeys want to tell you that there is a vertical tangent line there, and at the same time, there isn't a tangent line there, because infinity is not strictly speaking a limit. And yet if you open up a textbook, you'll often see junk like this. Limit of 1 over x as x approaches 0 is equal to infinity. Well, that's just totally wrong. That means there is no limit. Okay? There is no limit. It just doesn't exist. So, coming back to this again, we've seen quite a few examples, and this definition here, this finite difference, which is what is being calculated here, approaches a certain limit. But in this case here, there is no limit, because that is a point of inflection. Okay? If we move it away, then there is a limit, and we can get more or less that limit, but still, this difference quotient is never a descriptor of the tangent line. Just as the fake and bogus calculus has this particular definition of derivative, which is flawed for many reasons. Okay, This definition here is a load of garbage. Okay, so this is what modern mathematics or the bogus calculus is built on, this definition. Well, I think I've covered pretty much everything that needs to be covered, and want to warn you against reading articles in Wikipedia, which is completely unreliable. It's written by a select group of editors who will publish only what they think is correct, and say stupid things like, you know, it has been dismissed and have no particular source to back that up. It's just really hearsay. It was never dismissed. Only the morons in today's academia never understood what it means to be a tangent line. It's quite frightening when you think about all the ill-formed definitions in calculus and how it developed on flawed ideas such as infinity, limits, and infinitesimals. All of those ideas are deeply flawed. And of course, there's nothing wrong with inflection points not having a tangent line. The reason they don't have a tangent line can be seen if one studies these particular curves. Okay, so if it's a vertical, if it's a point of inflection on a vertical tangent, then of course it's not going to have a slope, because vertical lines, thanks to Newton, don't have slopes anymore. But guess what? In ancient Greece, a vertical line did have a slope. Its slope is that angle there, which happens to be one right angle, or 90 degrees. So in terms of degrees, even the straight line has a slope. It has a slope of 90 degrees. But smart Alec Newton changed that from angle, from slope determined in terms of angle, to slope determined in terms of ratio. And so when you want to determine the ratio, you end up with an undefined value. Okay, because the slope is really the rise over the run, and there is no run, it's zero. And supposedly anything divided by zero gives you infinity. That's part of the contribution that Euler made to mathematics. Euler thought that when divided by zero is equal to infinity, which is also, of course, absolute rubbish. But this is just how morons have built all this irrelevant theory, and it needs to be changed for the sake of progress in mathematics. But having said all that, watch what you read in Wikipedia articles. They're usually nonsense and unreliable. And if you have any questions, I'd advise you to join my new calculus group. It's on a different link, which I'll provide when I upload the video. And I'll also provide a copy of this applet which you could download and experiment with to see why it's a very bad idea to define a tangent line like this as the limit of these finite different ratios, because they never define the slope of the tangent line ever in any particular situation, whether it's an inflection point or otherwise. This never defines a tangent line or the slope of a tangent line. Well, this is a new calculus channel. My name is John Gabriel, and I hope you've enjoyed this video, and will join me again in the future for more videos revealing the ignorance and stupidity of modern academics and modern mathematicians. Till next time, goodbye.